Okay, let's unpack this plastic waste. It's a monster of a problem, isn't it?
It really is. Just the scale of it.
We're talking hundreds of millions of tons just clogging up the planet. Think back, 2008, it was already 245 million tons a year.
Wow.
Yeah. And the third biggest chunk of all our discarded stuff, municipal industrial waste.
And the environmental cost is huge.
Oh,
We see marine life getting tangled.
terrible. And those invasive species hitching rides across oceans on plastic debris.
Right. And even the risk to groundwater. That's pretty serious.
It is. But here's a thought, maybe a pivot. What if we could see all that plastic, not just as garbage, but as, I don't know, an untapped resource?
Like potential energy just sitting there.
Exactly.
You
Waiting
do.
to be unlocked.
Well, that leads us to something really fascinating. The possibility of transforming this environmental headache into something genuinely valuable. Fuel.
Fuel from plastic.
Yes, and the process that makes this possible is called pyrolysis.
Pyrolysis. Okay, sounds technical, but break it down for us. Simple terms.
Sure. So at its heart, pyrolysis is about using intense heat, really high heat,
Okay.
to break down organic materials. And that definitely includes all those mountains of plastic we were just talking about.
So you heat it up.
You heat it up significantly, yeah. Anywhere from, say, 400 up to maybe 1,000 degrees Celsius.
That's hot.
Very. But here's the crucial bit. The difference from just burning it.
Uh-huh.
It happens without oxygen
Yeah.
in an oxygen-free environment.
Okay. So
Right.
no burning, no combustion.
Exactly. Instead, the plastic undergoes this thermal breakdown, a decomposition using heat.
Got it. No flames, just heat, no oxygen. What happens then? What do you get out of it?
Well, the breakdown gives you a mix of three main things. You get
Hmm.
gases,
Okay.
you get a liquid, which we call oil, that's the potential fuel,
Right.
and you also get a solid residue. It's often called char.
Gas, liquid oil, and solid char.
That's the mix. And it's worth noting, too, this usually happens at lower temperatures than, say, traditional waste incineration.
Interesting. So it's a more controlled decomposition. Now, for this deep dive, we've really dug into a stack of research papers on this.
We have lots of different studies.
So what are the big questions these scientists are tackling? What are they trying to figure out about this plastic to fuel idea?
Well, the research covers a lot of ground. You see studies looking at how different types of plastic react.
Right, because not all plastic is the same.
Exactly. They look at the specific setups they use, the equipment, the conditions, and really importantly, the actual properties of the fuel they managed to produce.
Makes sense. You need to know if it's actually usable fuel.
Absolutely. And the sources, they also dive deeper into the fundamental chemistry involved,
Okay.
the chemical reactions happening. They investigate different designs for the reactors, the containers where the pyrolysis happens, and they analyze the quality, the makeup of those hydrocarbon liquids produced.
Okay, so a lot of different angles. If you had to boil it down, what's the core insight for, for someone listening? Why stick with us for this?
I think connecting it back, this deep dive is a really efficient way to get your head around this innovative approach to a massive global problem.
A shortcut to understanding it.
Pretty much. We're going to uncover some, frankly, surprising facts about how it works and the real potential of the fuel you can get. And we'll try to do it without getting totally lost in the technical weeds.
Sounds good, like getting up to speed quickly on something potentially game-changing.
That's the idea.
All right, let's get into the nuts and bolts then. How does this pyrolysis thing actually work? Give us the mental picture.
Okay, right. Imagine you take a bunch of plastic waste, could be different types. You feed it into a special container, that's the reactor.
Okay.
This reactor gets heated up, high temperatures. But remember, critically, no oxygen inside.
No oxygen, got it.
As that heat builds up, the plastic, which is essentially made of these really long chains of molecules, polymers,
Right.
starts to break down. It melts, then vaporizes, turns into a gas or vapor.
Okay, so it becomes vapor. Then what?
Then those hot vapors are channeled out of the reactor and into something called a condenser.
A condenser. Like you see in a chemistry lab, cooling coils.
Exactly like that. The condenser cools those vapors right down.
And they turn back into liquid.
Precisely. They condense back into a liquid. And that is the oil, the fuel oil we're talking about.
The main prize.
Often, yes. But it's important to remember that's not the only thing produced.
Ah, right. You mentioned gas and char, too.
Exactly. Some of the plastic breaks down further into gases that don't condense. And a portion usually remains as a solid kind of carbon-rich material. That's the char or residue.
So the final output is actually a mix.
It is. And the exact amounts you get, how much gas versus liquid versus char, that really depends on things like how fast you heat the plastic and the final temperature you reach.
So it's a bit like cooking, isn't it? Different temperatures, different times, you get different results.
That's a really good analogy, actually. Yeah. And the key chemical process going on here is called thermal cracking.
Thermal crack.
Think of those long polymer chains in the plastic like, I don't know, long, complex Lego structures. Thermal cracking is like shaking those structures so hard they break apart into smaller, simpler Lego pieces.
Ah, I see. Breaking the long chains into shorter ones.
Exactly. And those shorter pieces are the different hydrocarbon molecules that make up the fuel. And what's interesting is that higher temperatures generally make this cracking happen faster. You get more breaking down into those shorter chains.
More intense shaking, more smaller pieces.
Got it. Now, we keep saying plastic waste, but is all plastic created equal here? Can you just chuck any old plastic bottle or bag in?
That's a really important question. The short answer is no, not quite. While lots of different plastics can be pyrolyzed, some are definitely more suitable or easier to process than others.
Okay. Which ones work best?
The research often highlights thermoplastics. Things like polyethylene, that's your common plastic bags, some bottles.
PE.
Yeah, PE. Then polypropylene, or PP. You find that in food containers, car parts.
Polystyrene, PS think styrofoam, packing peanuts, and even PVC, polyvinyl chloride, which is used a lot in pipes and construction.
So those are kind of the main targets for this process.
Generally, yeah. They tend to break down reasonably well. However, the sources really stress that sorting the plastics properly beforehand is a big help.
Why is sorting so important?
Well, PVC is a key example. If you have a lot of PVC mixed in with other plastics, its breakdown can release chlorine compounds.
Ah, and chlorine can be corrosive.
Exactly. It can cause corrosion problems inside the reactor, damage the equipment over time. So separating out PVC, or at least limiting its amount, is often recommended.
That makes total sense. You don't want your fancy recycling machine eating itself from the inside out.
Definitely not.
What about preparing the plastic before it goes into the reactor? Just load it in as is? Or does it need prepping?
No. There's usually some important pretreatment needed. The research really emphasizes this.
Like what?
Typically, cleaning it first. Get rid of dirt, food scraps, other contaminants.
Okay.
Then size reduction is key.
Chopping it up?
Yeah, cutting it, shredding it into smaller, more uniform pieces. The papers mention sizes like maybe 1 by 3 centimeters, like small postage stamps.
Why is that important?
It helps it feed into the reactor smoothly, increases the surface area for heating, makes the process more efficient, and finally, drying it, removing moisture.
Right, because water would just turn to steam and mess things up.
Pretty much.
Yeah.
It consumes energy and can interfere with the process. So, yeah, think of it like prepping ingredients before cooking. Clean, chop, dry. Makes everything work better.
Clean, chop, dry. Got it. Okay, so we have our prepped plastic ready to go. Now, tell us about the reactors themselves, these specialized containers. You mentioned different types.
Absolutely. The research describes a few main designs. A common one is the fixed bed reactor.
Fixed bed.
Yeah. Basically, the plastic sits in a stationary bed inside the reactor. These are often stainless steel. They can be used for just thermal pyrolysis heat only, or with catalysts, which we can talk about later.
Okay, what else?
Then you have fluidized bed reactors. These are quite interesting.
How do they work?
They use a flow of hot gas from below to lift and suspend the small plastic particles. It creates a sort of bubbling, fluid-like state.
Ah, so the plastic pieces are moving around.
Exactly. And that constant movement gives you really good, really efficient heat transfer throughout all the plastic.
I see. And any others?
The sources also mention rotary kiln reactors. You see these more in larger commercial scale operations sometimes.
Rotary kiln, like a big rotating drum.
Pretty much. A slowly rotating cylinder, usually tilted slightly. The plastic tumbles through it as it heats up and pyrolyzes.
So different designs for different needs, different scales. Makes sense. What about the timing? Is it like you load a batch, run it, empty it, repeat, or can it run continuously?
Both approaches exist.
Yeah.
You definitely see batch processes described, especially in lab settings or smaller scale tests. You load it, cook it, unload it.
Okay.
But for larger industrial applications, continuous processes are usually the goal.
Where plastic is constantly going in one end.
And the products, oil, gas, char, are constantly coming out the other end. It's designed to run nonstop, which is generally more efficient for large volumes.
Right. Now, temperature. We touched on this 400 to 1,000 C, but often maybe 400, 550 C. Does the ideal temperature change depending on the plastic or what you want to make?
It definitely varies, yes. The type of plastic matters, and critically, what end products you're aiming for.
How so?
Well, the research clearly shows that temperature has a huge impact on the product distribution. That mix of gas, liquid, and char.
Okay. Example.
For instance, cranking up the temperature generally leads to more gas being produced. The heat causes more intense cracking into very small molecules.
So higher heat equals more gas, less liquid fuel, potentially.
Often, yes.
Yeah.
So you need to find the sweet spot depending on whether you want to maximize oil production or perhaps produce more gas for energy use.
Okay. What about how quickly you heat the plastic? Does that matter? The outline mentions slow versus fast pyrolysis.
Oh, absolutely. Heating rate is another crucial parameter. It makes a big difference. So slow pyrolysis means heating the plastic up relatively gradually. This approach tends to favor the production of more solid char.
More char with slow heating. Okay.
Conversely, fast pyrolysis, or even flash pyrolysis, involves heating the plastic extremely quickly. Very rapid temperature increase.
And what does that do?
These faster heating rates generally push the reaction towards producing more liquids, the oil, and also more gases, less char.
Interesting. So fast heat gives more oil and gas.
Generally speaking, yes. Think of it maybe like roasting vegetables. A long, slow roast might yield something different than a quick, high-heat sear. Different compounds are formed or released.
That makes sense. And how long the plastic actually stays hot in the reactor? Residence time, is that the term?
Exactly, residence time. The duration the material spends at the pyrolysis temperature.
How does that affect things?
Longer residence times can lead to something called secondary cracking.
Secondary cracking. Cracking the cracked stuff.
Pretty much. The initial products of pyrolysis, those first hydrocarbon chains formed, if they hang around in the hot zone for too long, they can break down even further into even lighter, shorter hydrocarbon chains.
So the Lego pieces break into even tinier pieces.
That's a great way to put it. So adjusting residence time is another way to influence the final composition of the fuel you get. More secondary cracking might mean more gasoline-like components, perhaps, or more gas.
So many variables to control. Temperature, heating rate, residence time.
It's definitely a balancing act to optimize the process.
Okay, one last process detail from the outline. Vacuum conditions. Why would you run this whole thing under vacuum?
Yes. Using a vacuum can offer a couple of key advantages.
Like what?
Well, firstly, it's another way to ensure that absolutely no oxygen gets into the reactor. We keep saying oxygen-free is crucial.
Right, for pyrolysis, not combustion.
Exactly. A vacuum guarantees that. Secondly, the research suggests vacuum conditions might actually help increase the yield of the liquid oil.
Oh, how does that work?
By lowering the pressure inside the reactor, the vapors that form as the plastic breaks down can escape the hot zone much more quickly.
They get sucked out faster.
Essentially, yes. This reduces the time they spend at high temperature, which potentially minimizes that secondary cracking we just talked about, the breakdown into gases.
So less chance for the valuable oil vapors to break down further.
Precisely. It's like giving those valuable vapors a quick exit ramp before they degrade into less desirable products, maximizing the liquid you can condense and collect.
Clever. Giving the good stuff a faster escape route. Okay, now let's shift gears slightly. Catalysts. You mentioned them briefly. What role do these helpers play?
Right, catalysts. This is where the process optimization gets really interesting, I think.
How so?
So catalysts are substances that can speed up chemical reactions.
Right.
Or allow them to happen at lower temperatures without being used up in the reaction themselves.
Okay. And in plastic pyrolysis?
They can offer some really significant benefits. The research shows they can potentially lower the required pyrolysis temperature.
Which saves energy.
Exactly. Less heat needed. They can also reduce the reaction time, make the whole process faster.
Faster and cooler. Sounds good.
And perhaps most importantly, they can really influence the distribution of the products.
Meaning you get more oil or more gas or specific types of molecules?
Precisely. You can potentially steer the reaction to produce more of the specific fuel components you want. It's not just random breakdown. You're trying to guide it chemically.
So it's like adding a special ingredient to your recipe to get a specific flavor or texture.
That's a perfect analogy. The catalyst is like that key ingredient, potentially giving you a fuel richer in, say, gasoline range molecules or diesel range molecules.
Fascinating. So what kind of catalysts are we talking about? The outline had some specific names, ZSM5.
Yes, zeolite-based catalysts are mentioned a lot in the papers. ZSM5 is a common one.
What's special about zeolites?
They have these really unique porous structures, like microscopic honeycombs with acidic sites inside. These structures and acid sites are great at promoting the cracking reactions. They can increase the formation of olefins, for example, which are valuable both as fuel components and chemical feedstocks.
Got it. What else was tested? Activated carbon.
Activated carbon, yeah. It was tested, showed some success, particularly with virgin polypropylene, especially when they used a specific type of horizontal condenser setup.
Interesting. And baking soda. Sodium bicarbonate. Seriously.
That's surprising, doesn't it?
Mm-hmm.
But yes, one study found that sodium bicarbonate actually gave a higher fuel yield when used with waste plastic compared to virgin plastic, and it reduced the residence time needed.
Baking soda. That's amazing. A common household item playing a role here.
It is quite remarkable. And the research even drills down into different types of zeolites. They mentioned codes like NKC3A, NKC5, NKC7.
And they behave differently.
They did. When tested with LDPE, that's low-density polyethylene, like film wrap, they found NKC5, for instance, tended to promote the formation of aromatic compounds and reduce the amount of alkanes, another type of hydrocarbon, in the final liquid. So the specific catalyst choice can really fine-tune the fuel's properties.
Wow. So much control potentially. Okay, so after all this heat, cracking, maybe some catalytic help, what is this fuel oil actually like? What does it look like? And crucially, how good is it as a fuel?
Right. Well, appearance-wise, the research typically describes it as yellow-brown.
Okay.
Sometimes it can apparently be a bit creamy or waxy, especially if the heavier components haven't been separated out effectively during condensation.
Waxy, huh?
Yeah. And a key point the papers make is that this initial oil you get, it's often quite similar to crude oil.
Raw crude oil, not like finished gasoline or diesel.
Exactly. Which means it usually can't just be pumped straight into a car. It generally needs refining.
Ah, okay. Just
Right.
like crude from the ground.
Pretty much. You need to remove impurities, maybe some leftover ash or those waxes we mentioned, things that came from the original plastic or additives.
So it needs processing. How do they refine it?
Distillation is the common method mentioned, using something like a bubble cap tray column.
Like in an oil refinery.
Similar principle, yes. It separates the oil into different fractions based on their boiling points. You can separate out lighter fractions like gasoline, medium ones like diesel, and heavier ones.
Makes sense. So once it's potentially refined, what properties do scientists measure to judge its quality?
They look at a whole range of standard fuel properties. A really important one is the calorific value.
Energy content, basically.
Exactly. How much energy you get when you burn it. The potential looks good here. One paper estimated around 43.3 megajoules per kilogram for fuel from polyethylene. That's pretty high in the range of conventional fuels.
That is high. What else?
They measure density-specific gravity and API gravity. These help compare it to water and standard petroleum products.
Okay.
Viscosity is another big one.
How easily it flows.
Yes. Crucial for how it behaves in an engine. Fuel pumps, injectors. They often use things called redwood viscosity meters to measure this.
Right. So energy density, flow. What about safety and performance?
Definitely. Flashpoint and firepoint are key safety metrics.
The temperatures where it ignites.
Right. Flashpoint is where the vapors ignite briefly. Firepoint is where it sustains burning. One experiment reported a flashpoint of 420 Celsius, firepoint 480 C for their pyrolytic fuel.
Okay. And engine performance indicators, like octane for gasoline.
Exactly. They measure octane number for gasoline-like fractions, which indicates resistance to engine knocking, and cetane number for diesel-like fractions, which relates to ignition quality.
And how do these numbers look for plastic-derived fuel?
It varies. The research notes that the pyrolysis temperature and where you collect the fraction from the distillation column really influence these. Higher octane is better for gasoline, higher cetane for diesel. One interesting note was that thermal pyrolysis, just using heat without catalysts, often results in liquids with fairly low octane values.
So maybe not ideal for high-performance gasoline right off the bat.
Potentially not, without more refining or maybe using specific catalysts during pyrolysis to boost it.
I see. And they also look at the actual molecules in the fuel. The outline mentioned PNA.
Yes, PANHEA analysis. It stands for paraffins, olefins, naphtha, or naphthanese, and aromatics.
So the different types of hydrocarbon families.
Exactly. It's like a chemical fingerprint of the fuel. The relative amounts of these different hydrocarbon types dictate the fuel's overall properties, its stability, its combustion characteristics, everything.
And does the pyrolysis process affect this mix?
Absolutely. For example, higher pyrolysis temperatures might lead to more aromatic compounds being formed, and catalysts, as we discussed, can significantly shift this PNA distribution.
Okay. And how does this plastic fuel generally compare to, say, regular diesel?
The research often draws direct comparisons. There are similarities, but also differences. For instance, fuel made from LDPE might have a higher content of olefins or alkenes compared to standard diesel.
And what does that mean?
Well, higher alkene content can sometimes affect the fuel's long-term storage stability. It might be more prone to oxidation or gum formation over time.
So promising, but maybe needs careful handling or additives like conventional fuels sometimes do?
Potentially, yes. It highlights that while it's similar to fossil fuels, it's not always identical, and those differences need to be understood.
Right. Let's talk yield. How much fuel can you actually get? What's the efficiency like? This brings us back to that trash to treasure idea. Is it actually efficient?
The numbers reported in the studies are definitely encouraging on that front.
Such as?
Well, one study recovered 833 milliliters of oil. That's liquid fuel from every kilogram of type 6 waste plastic they processed.
Wow, that's over 80% by volume, roughly?
Yeah, and they calculated a conversion efficiency of 78.1%,
Mm-hmm.
and importantly, a waste reduction efficiency of 94.3%. You're getting rid of almost all the plastic mass.
That's huge waste reduction and typical oil yields overall.
The sources suggest that typical total fuel oil yields from pyrolysis are often in the range of 50 to 65% by weight.
Still pretty significant. Half or more of the plastic weight turned into oil.
Exactly. And remember the catalysts. Using something like that sodium bicarbonate we mentioned earlier, one experiment hit a conversion rate of up to 92.33% with waste plastic.
Incredible. So catalysts can potentially push yields even higher.
It certainly seems possible based on the research.
Those are impressive figures. You're drastically cutting waste and getting a substantial amount of usable fuel energy back. Seems like a win-win.
It really does frame it that way, doesn't it?
Okay, so we've mostly talked about lab setups or maybe pilot scales. What about scaling this up? Are there real continuous pyrolysis plants operating?
The research does describe the design concepts and sometimes pilot testing of semi-scale continuous plants.
Semi-scale, so bigger than a lab bench, but maybe not full refinery size yet.
Exactly. These plants are specifically designed to try and maximize the production of certain fuel types. Often diesel range products seem to be a focus.
And what do these continuous plants look like?
They're more complex, as you'd expect. They need sophisticated feeding systems, maybe pre-melting the plastic or using extruders to feed it in consistently.
Right, you need smooth input.
Then the pyrolysis reactor itself, of course. And after that, crucial separation sections, usually involving distillation columns and condensers to separate out the different fuel fractions continuously.
So you can pull off diesel, maybe some lighter gasoline-like stuff, waxes, and handle the gases separately.
That's the idea, to get consistent streams of different products.
Sounds complex, but necessary for producing fuel reliably at scale. What are the big challenges in designing and running these?
Well, there are definitely significant engineering hurdles.
Yeah.
Preventing leaks is a major one. You're dealing with hot vapors, potentially flammable gases. You need the system sealed tight, no air getting in, no vapors getting out unexpectedly.
Safety and efficiency, right?
Absolutely. And precisely controlling the feed rate of the plastic and the temperatures throughout the entire system is critical for getting consistent product quality.
Tricky to keep everything stable.
It can be. The research also mentions things like managing the temperature gradient correctly. You don't want the plastic starting to break down in the feeding system before it even properly enters the main reactor zone.
Ah, so you need controlled heating only where you want it.
Exactly. Lots of process control challenges to solve for reliable, large-scale operation.
Okay, wow. We've covered a lot of ground here, from the basic chemistry to reactor designs and fuel properties. Let's try to summarize. What are the absolute key takeaways for you, for our listeners?
I think the main thing is that pyrolysis genuinely looks like a very promising and technically viable way to tackle a huge waste problem plastic and turn it into a valuable energy resource.
Fuel, turning trash into fuel is real.
It seems to be. And we've seen just how much the details matter. The specific plastic you use, process conditions, temperature, heating rate, residence time, they all have a massive impact.
And the catalysts.
And especially catalysts, yes. They can really influence both the yield, how much fuel you get, and the quality, what kind of fuel it is. And importantly, the research suggests there's a real potential energy profit here. You get more energy out than you put in to run the process.
That's a critical point for viability. Okay, so lots of potential, but what questions remain? What should we still be thinking about or looking into?
That's a great point. While the science is promising, there are definitely big questions still hovering.
Jazz.
Well, the real-world economics. What's the true cost of building and running these plants on a massive scale versus the value of the fuel produced? Is it competitive?
Economic feasibility. Crucial.
Right. And how do we best refine this pyrolytic oil to consistently meet the very strict specifications required for modern vehicle fuels? That's still a challenge.
Getting it from crude-like oil to pump-ready fuel reliably?
Exactly. And beyond just reducing the volume of waste going to landfill, what's the full environmental picture of the pyrolysis process itself?
You mean, are there emissions? Other byproducts?
Precisely. We need to make sure we're not solving one problem by creating another. Careful management of any emissions or residues is essential.
Good point. So listeners can maybe look into companies or research groups actually doing this work now.
Yeah, that'd be a great next step to see the cutting edge and how these challenges are being addressed in practice.
Some really important considerations there. Okay, to wrap this all up, give us one final provocative thought to leave us with. Looking ahead, what's the bigger picture for this kind of tech?
It's fascinating to think about, isn't it? The potential shift.
Yeah.
Well, here's something to chew on. We live in a world that's increasingly pushing for circular economies, trying to reduce waste, trying to lessen our dependence on digging fossil fuels out of the ground.
Right, the big transitions we talk about.
So, could it be? Could our overflowing trash cans, literally stuffed with all this discarded plastic, could they actually become the oil wells of the future?
Wow, our trash cans as oil wells.
It's a pretty radical thought, but it's the kind of future this technology, plastic pyrolysis, invites us to at least consider. A fundamentally different way of looking at waste and resources.